So Sam was at the University of Edinburgh, and you're now a consultant.
Yes, I am. I'm still a visitor at Edinburgh. HAFDAL over there is still a PhD student.
Right. Okay, very good. And to talk about what you did a few years ago.
Donkeys years ago.
Yeah, a reflection about that work. Okay.
Yes, a reflection. Yes. So this is a topic that presented 4 years ago when I was young and wrinkle-free at ISMM on prefetching in functional languages. So basically, I added software prefetching to OCaml and just kicked the tires a bit. And this talk is not really about the software prefetching itself. It is a little bit, but it's really more about that tire kicking exercise and all of the things that we learned about how functional programming languages interact with microarchitecture, because really I'm a microarchitect anyway. So let's go through some slides. Please do talk to me, interrupt me, ask me questions throughout. It will make more sense if you do. So let's see where we get. Right, so motivation. Everybody knows functional data structures are scary. What I mean by that is, if we look over on the left, we've got those nice prefetchable arrays, right? What I mean by that is that arrays have lots of memory level parallelism. We know exactly where we're going in an array. We know we're going to be accessing each of these elements in the future. We can see it. Not only can a stride prefetcher see that we're going 1, 2, 3, 4, 5, but the out of order engine also knows where we're going and can just keep going ahead and fetching more stuff. What about linked lists or trees? Because if you are writing in a pure functional language, that's what you're stuck with, right? Okay, you can use arrays in something like OCaml, and the code basically ends up looking like C, and so it's not that interesting from this point of view. What about these structures? Well, your linked list has no memory level parallelism at all, right? If you want to work out where you are in 5 elements time, you have to walk 1, 2, 3, and 4 first. There's not a lot you can do with that. You might think that, okay, when we reach this iteration here, well, maybe we'd best prefetch this one before we finish working on this. But bear in mind, you're going to be on an out of order processor anyway, most likely. It's already there. The out of order core is already there by the time you try and do anything else. So there's nothing productive you can do. The same is true for the tree, right? Yes, you have 2 nodes that you might be able to go to, and you might be able to work out which one, and you can maybe fetch the next. But your out of order processor will have already worked it out by the time you try and do anything more elaborate. If you try and fetch both, it's going to just become super inaccurate, exponentially so as you go down this data structure. There's not a lot you can do, right? And one answer to that is, if there's nothing you can do, if there's no memory level parallelism, then you just look at what you did in the past and repeat it. And if it's the same pattern, then you can look ahead that way. And when I was starting this work, I expected the answer was going to be naughty, naughty. If you're in functional languages, there's no memory level parallelism. The best you can do is temporal prefetching. And these days, that's not that bad of an answer, actually, because temporal prefetching has become viable in real microarchitectures relatively recently. If you look at what ARM are doing with their cache mischaining prefetcher, that sort of thing where they spot patterns and repeat them, that now actually happens. So there are bits of hardware in here that do help us with the sort of linked data structures you see in functional programming languages today, right? In microarchitecture, new developments since I first wrote this paper, actually. The reason that isn't the moral of this talk, though, is because linked lists aren't actually as bad as you expect. So what we've got here is, this is an example of a fold left, which is it's just an iteration operation over a linked list. I choose this one because it happens to be nice and tail recursive, so it doesn't do anything much more than add these things together and walk the linked list. Note that what we've got here are tuples. We're adding together tuples. The reason I'm doing that is because in OCaml, the language we were focused on, tuples get boxed and so get access via pointer indirection. If you're just doing an integer, it will stay inside here, be unboxed inside the linked list itself. And that's important. That's important for what we're about to do with this data structure, or what's about to happen to this data structure from underneath us. Right. So that's this setup. And what we see here is we've got 2 versions, right, of the same code, one on arrays, one on linked lists. And we've got two things going on here. First is that if we access the thing in the order it was allocated, if we just allocate a load of random data and then walk it, this is where the performance is. If we sort that data first, this is where the performance is, like 6 times slower, right? So there's something weird going on there that we need to explore. The other thing you should notice that is perhaps even weirder is that the list version isn't really that much slower than the array version. And yet I've told you that there's no memory level parallelism from these lists at all, and that your performance is going to be terrible and woe is your hardware. Right, so our next clue as to what is going on here is if we look at list.item, which is a very similar bit of code base, with or without the hardware prefetcher enabled, right? So you've got this hardware stride prefetcher in your code, not the temporal prefetcher we're talking about. Hardware stride prefetchers look for regular address patterns and just keep going. They've been there forever. And you can turn them off in Intel's cores, and we did. And look at what happens here. You see, this is, one is the normalization factor. The other two involve software prefetching, which we'll talk about in a bit. But note that without the hardware prefetcher turned on, the list actually slows down more than the array does. And yet I've told you this hardware prefetcher is for finding regular patterns like the sort that you get in arrays. And yet it's the linked list that's slowing down more when you turn it off. The other thing is that actually we are able to software prefetch this really well, and I'll show you how in a second. So what we've got to do to unpick is, the first thing is that the hardware prefetcher has got to be picking up this linked list somehow, right? There's no other explanation for this. The second thing is about then, okay, so why isn't the array slowing down as much? And that is to do with out of order execution. The fact that in a modern processor, you fetch instructions speculatively in order, you commit them in order, but in the middle, it all gets reordered to try and find independent work. And as I explained earlier, for an array, you've got lots of independent work. For a linked list, you've got no independent work, at least as far as this engine is concerned, because this sees all of the data dependencies that are truly there, right? It sees that there's a data dependency between each linked list, so it has to keep walking them all before it knows where to go. Not true of your stride prefetcher, though. Your stride prefetcher is just doing value prediction on the addresses that it's getting it. And as it turns out, if you ask for a linked list like this, where do you think your allocator will put each of these elements? And the answer is right next to each other. You're allocating these things. They end up next to each other when you allocate them, if you allocate them one after the other. It might not be quite that simple if you've got a more complicated data structure, but it's not going to be that far off either, especially because if you're in something like OCaml, you'll have a generational garbage collector that it will first allocate it into a sort of little pool, but then it will garbage collect them out to another pool where it will move them. And then they will end up really nice and sequential. And so your stride prefetcher will basically see this as, it's just an array, isn't it? So I can prefetch it the same way. And you, as the programmer, as I've said, we can actually software prefetch this as well. You can do the same thing. We added software prefetch instructions to OCaml. We also added a special software prefetch that doesn't just prefetch the pointer. So here, we're not prefetching the pointer to head. We're prefetching the pointer to head with an offset. So we sort of jump over here somewhere and say, I'm not saying that you're probably going to access this, even though I know that, but you know that already. Try accessing something over here as well. Just see if it works, right? And you don't even get access to the exact array. This is all still in the functional world where this isn't C. You don't get access to the exact address that you're after, but you say, whatever that address is, just prefetch me something just a little bit further on. And you get massive speedups, right? And this is even with the hardware prefetcher still turned on. This is for list.nth, which is the simplest case, right, where you just want the nth element of a linked list. It doesn't actually matter what type that linked list is because you never access its elements. You just walk the linked list for n elements. And you get really massive speedups, even with the hardware prefetcher turned on, which, given that we know you get massive slowdowns when you turn the prefetcher off, this is saying that the prefetcher is picking it up, but it's just not quite aggressive enough. It's not looking ahead quite far enough for this sort of code. The other thing to unpick here is actually we've got 3 different cores that we're looking at here. Haswell is a now admittedly quite old generic out-of-order superscalar, something that you've had on your desktop. A53 is an in-order core, and you get very different effects from those. And Knight's Landing is out of order, but little, right? That's a Xeon Phi core. It's small, it's a bit out of order. And we'll see in a few slides that you get very different effects from these 3 architectures as a result of adding prefetching code into the application because their bottlenecks are different. Right. So what I've said is for a linked list, you'll be accessing it sequentially. And for an unsorted list, these things that we're boxing off to will also have been allocated in the same order. They'll be accessed in the same way. It will be regular. Your stride prefetch will pick it up pretty well. And performance will be good. However, when you sort it, think about what happens to the data structure. Bearing in mind this is OCaml, so it's functionally pure. Actually, you end up with a brand new linked list, right? You can't change the links in the old one. That's not allowed. So you end up with a new linked list, and that new linked list ends up roughly sequential in memory because you've reallocated it. But and the old one gets garbage collected away, right? It disappears. The old one with the links that were there before, the nice ones that go straight up. These won't get reallocated, right? These are the same old objects that were there before. That's allowed in a pure language. So we end up with this sort of nasty pattern here, where though this axis is quite nice, this axis isn't, right? We've got this one is just traversing all around memory. It's going to miss and miss and miss in the cache. Your prefetcher is not going to be able to tell what to do. Your hardware prefetcher, your hardware stride prefetcher won't know what's going on.
And what if this is going to come back and move to another?
So this is assuming that that all of the garbage collection is happening, right? These won't get garbage collected. By this point, they will probably be on the heap where they stay. You could say that maybe if this gets garbage collected again by a generational garbage collector that has a different decision about where it should place these, if there's a sort of movement phase, these might end up rearranged. We didn't find that in OCaml. We sort of found it in Haskell, but Haskell was never faster than OCaml. But if you looked at performance counters, it wasn't because of memory misses. But it was really easy to mess up the ordering that Haskell wanted, right? So if you had sort of 2 linked lists live at the same time with different pointers into this, both would end up horrible. And data movement like that has its cost as well, right? It's something that you often want to avoid unless you really have to do it. When you have direct allocation, that ends up being the most expensive thing often in all of this sort of code. Even lots of stack allocation. I gave the example of fold left earlier because fold right isn't tail recursive, and that means that you spend a load of time just like adding stuff to the stack. And that also means that you get less benefit. You still have benefits from prefetching, but you get less benefits from prefetching because it's kind of just not the main thing. The thing that you're prefetching isn't the main thing that's going on anymore.
So the main thing I was wondering is that whether maybe coupling it to the new generation actually undo ramming up.
It might do if it happens at the right time.
Yeah,
exactly. And so the way it works in OCaml is that there is a minor and a major heap, I think. And the minor heap's like 2 megabytes big. So as long as this data structure is big, it needs to be big for any prefetching to matter. Otherwise, it's just cacheable, right? And it will get moved into the major heap after you've allocated like 2 megabytes of stuff, and it will just stay there. You won't then regeneration it after that. If you did, you might get slightly different effects, but in the end, this will still come back to get you eventually. And that data movement isn't something that you want to do very often because it is expensive as well. We get a similar thing with arrays. Obviously, arrays, you always access them. They're always going to be a sequence, assuming you access it in a sequence. But the things you point to also get jumbled up in the exact same way. And the way that we prefetch this is not that different from what you do in imperative languages if it's an array because they're the same data structure, right? So what we have here is that we issue a prefetch to a few iterations ahead on this data structure. So we load this and use that to prefetch this. And then we also issue a prefetch for this. The way that works is that you're sort of staggering prefetches so that I've said you have to load this to work out what this is. So we also prefetch this earlier on so that by the time we're ready to load this to do the prefetch, we'll have prefetched this already so that we can prefetch this. So that by the time we're ready to load this, we can that will be in the cache as well. But you've got this sort of staggering thing where you prefetch ahead from one structure the full way, then half on the other data structure, and split things up like that. And you add these instruction to OCaml. It's basically just a C intrinsic. It's really very simple to add. With linked lists, you can't do the same trick, right? You can't walk ahead in a linked list explicitly. You have to do it or implicitly. You have to do it explicitly by just like traversing through everything. So what we've got in the simplest case is this kind of wacky pattern match thing here, where we pattern match out like 8 elements of this thing and say, okay, we've got our 8th element, prefetch that thing, and then on the next iteration, you do the exact same thing, right? So you walk 8 elements ahead again and prefetch that thing. And you can see that we're doing a load of wasted work here, right? We're repeatedly walking the same things to repeatedly get ourselves like 8 elements ahead so that we can issue a worthwhile prefetch that will be far enough ahead to hide memory latency. And you can do something about that, right? You can do it this way instead. It's even worse pattern match. This is like 32. I don't even think it's the right. No, it probably is the right code. 16, 32 elements ahead. And what we do here is we issue the prefetch and then we store the tail, right? So that then in the next, we do that in our first iterations, a special case. Then in our next iterations, we have this thing that we prepared earlier. We return this tail that we prepared earlier. We prefetch, we pattern match off the first element of that, prefetch that, and then return the next tail so that you can store it for the next. So when we get here, we store that. When we get there, we can then skip ahead to here and prefetch that, and so on and so forth. Yep.
So when you start, you have to manually go through the list, and that pattern match will actually manually walk it and load it, and that's a slow load.
It's a slowish load, yeah. All of these loads aren't horrendously slow because this linked list walk is hardware prefetchable. So it's not that bad, right? It's not like you're taking a full hit to main memory each time. And that's the only reason this works, right? If you were taking a full hit to main memory each of these times, there'd be fundamentally no way to get ahead of the program. Here, because it isn't that bad, you can get ahead of the program. It's more like compute overhead than memory overhead. This stuff all ends up cached nicely. But yeah, you take this compute hit for the first iteration, but then sort of goes away after that. And we also do the trick we talked about earlier where to make this walk itself, or at least this walk itself, less bad, we do this prefetching with offset so that we prefetch what we think will be the next few linked lists, assuming that it's going to be roughly linear in memory. It doesn't have to be perfect, it just has to be good enough, right? For the prefetch to be more good than bad. And what we get on Haswell is we get better improvements as we go up the complexity of the techniques, obviously, which does imply that for both array plus basic array prefetching is prefetching ahead in the array itself. Offset prefetching added to complex is prefetching ahead in the linked list itself. It implies for both of them that for this pattern, at least the hardware prefetcher is not quite aggressive enough. And that's something that you curiously see as being fairly consistent for anything that looks vaguely like this in any language on any processor ever. The hardware prefetcher isn't quite aggressive enough in these cases, and adding a software prefetching for the same thing is good. That software prefetch itself is really cheap as well. It's just one instruction, whereas the software prefetchers to do all the linked list stuff are understandably not one instruction. There are a lot of instructions, which means they're only good when they're worthwhile, and when they're not, they'll hurt you, and we'll see that in a minute. The other weird thing happening here is that there are actually 2 different cases on here, right? One is a simple sum. The other one is a sum that involves some hash computation. You can basically see it as sort of extra instructions that fill up the pipeline, dead work, that just split apart these memory accesses in the pipeline. And you'll note that on this out of order core, we start to get massive speedups when that happens. Even though the program that I've just described to you, this hash sum, the difference there is that that's more compute bound, isn't it? Because it's got more compute in it. And actually, we get a bigger speed up when it gets more compute bound, which is strange for prefetching, which is about memory bounds. And this is because it trips up the out of order core. Having more work to do means the out of order core is less good at parallelizing what we're giving it. And so our software prefetchers come into the fold. Again, that's something that you see quite generally on out of order cores. It's not a functional programming thing. Out of order execution. We see the pattern, the opposite pattern, the one you'd normally expect on the in order core, where adding in more compute makes it more compute bound and less prefetchable. That's just less confusing. For Knight's Landing, which is a bit out of order, but not very, we see a more extreme effect where actually the basic version of it slows down because the prefetchers are themselves expensive on compute, right? And you don't have a lot of it on this core that can do things, it can do out of order just well enough to parallelize its memory accesses, and everything else you add on top of that just makes things slower in the simplest cases. I'm going to skip these. These are about the distances that you have to fetch at. They're not that fiddly. You just have to get them far enough ahead to make this all work so that you can hide memory latency. Here's an example of how you do it for real programs. In this one with Quicksort, we basically, as well as sorted data being prefetchable, you can prefetch the sorting itself as well. With Quicksort, you have this linked list that you're walking, you split it into sublists, you prefetch the list as you walk it. With merge sort, you actually do the opposite because merge sort merges sublists into one. And so you prefetch each of these smaller lists simultaneously into the one merge list. It's just the opposite case, basically. It works quite nicely in both cases. You get pretty big speed ups across all of these architectures, apart from arrays on Night Landing, the small out of order Night's Landing, for reasons we've talked about already on arrays, where the extra instructions just cost you a lot. You don't see the same on linked lists because they're just really horrible. So the out of order core is not very good at it. Right, what does this, too far. What does all this mean for microarchitecture and compilers on functional languages? Well, for this workshop, out of order cores are bad at linked data structures, right? They just are. There's too many data dependencies. They aren't very good at going ahead of them. Hardware prefetchers are good at linked lists. Note the difference between linked data structures and linked lists. They're good at linked lists. They can value predict based on the address past data dependencies if the allocator does its job, right? Software prefetching can do much better, both in terms of regression and following new patterns that the hardware prefetcher just can't understand. And it has no hard state, right? So it actually is, you're doing this fairly low level thing, but it fits into functional languages quite well because it doesn't have any hard state. It's just a soft hint. It's kind of suitable for functional languages. But the correct software prefetch depends not only on the code, but on the data set distribution and size, so runtime information. You need a data set that's big enough to not fit in your cache, otherwise all of the extra instructions just slow you down. You need to fetch ahead in the right way. All of this stuff makes it just a real pain to use unless you really know what you're doing. And there's basically no avoiding that, right? Because you don't have the ability to react at runtime in the way that hardware prefetchers do. So, final thought of the talk, with a minute to go. Vector run ahead is a microarchitectural technique that I have, that we had at ISCA 21, Micro 23, and we got top picks for it, micro top picks for it twice. This is a microarchitectural technique that, so you've got this stride prefetcher that can, we've got this nasty pattern here, this is basically the same patterns we were looking at elsewhere. The stride prefetcher can predict ahead and fetch our array structure with all of the nasty pointers on it. Up until this point, you've not been able to do that in hardware only in software. Vector run ahead learns from the stride prefetcher and spawns sort of lots of copies of this A in vectors so that it can fetch all of them at once. If it's going to miss on each of these, it's better miss on them all at the same time to hide the latency. More details on that in those papers. The reason I mention it here is because, well, as far as your stride prefetcher is concerned, your linked list basically looks like an array. I've told you that already. So we can expect this exact same trick to work for functional languages. It's beyond out of order execution, right? It's using bits of value prediction that functional languages work well with while avoiding the out of order execution that they don't work well with, and using that to spawn things that get you memory level parallelism. This is a different paradigm. We designed it for imperative languages, but I think it's just as relevant for Alpha languages. Okay, so that's the talk. If you want to know more about this from a different perspective, watch my talk at ISMM, where I sort of weirdly look like the Mr. Burns alien from The Simpsons. Yeah, that's it. So thank you.
So you said most of your work is on OCaml, but you also hinted that you've done things like this for Haskell.
Right, yeah.
So-
So I looked briefly into Haskell because Haskell already. So we had to add the software prefetch into OCaml, but that was pretty easy. It's well documented and the code is nice. Haskell already has software prefetching in it, but I couldn't get it to type and it wasn't documented. So I couldn't use the software prefetch instruction in it, right? I just couldn't get it working. So I never ran an experiment with software prefetching, but you can infer things about its prefetchability just by looking at perfstat, right? You connect up perfstat, you can look at the MPKI of each of the caches. And so that's how I found out these things about how Haskell was runtime reordering things, but it wasn't always getting it right. It's a bit harder to work with Haskell because it's lazy, right?
Okay. Yeah.
With OCaml, it's really easy to work out a one-to-one correspondence with the assembly. You can tell what the access pattern is going to do. Whereas in Haskell, there are cases where this will work, but it's more difficult to guess what is going to go on at the program level.
Right.
You don't know whether it's going to be run strict or lazy, depending on the exact details.
That's what I wondered about, actually, the difference, whether the laziness complicate things.
Yeah, I mean, obviously, a lot of the time, strictness analysis means it does run the way you expect if it were strict, but it's complicated.
I was going to say another way of phrasing that question is perhaps that the access order needs to be similar to the allocation order. Is that the case?
Well, it's that for the linked list itself, it's sort of the opposite, right? So what I'm arguing is that in Haskell, just as in OCaml, the linked list itself kind of will have to end up in allocation order. There's basically no way to construct in a pure language. There's basically no way to construct a list that isn't roughly sequential. It doesn't need to be perfectly sequential. I mean,
Oh yes,
the reason I chose, well, so you may ask, the reason I chose the example of these sorting algorithms, right, is because the sort of counterexample is these sorting algorithms, right, where you start adding things on at different points into these lists. In both cases, you add things into these linked lists at different times, so they aren't truly created sequentially. And you start adding things onto bits of lists that you prepared earlier, but it's still roughly sequential, right? There will be discontinuities, but there will be more continuities than discontinuities, especially once you get into generational garbage collection, where you'll have whole blocks of stuff moved across at once. So it doesn't need to be perfect, right? It just needs to be good enough.
Yeah, once you've gone through one collection, you'll tend to.
Yeah, exactly. And actually, it's kind of the opposite, right? That with all of the data that you're pointing to, software prefetching is good when that isn't allocated sequentially. So it's when you start getting some jumbling up that this starts to work the best. If that makes sense.
So at the start, you sort of teased a binary tree, right? So linked list, the spine is nice and linear. How does this look with the binary tree? What do you well, obviously, okay, so there's nothing you can do.
Apart from history prefetching, right? There's no memory level parallelism. You don't know where you're going until you do the compute, and there's not a lot you can do, except from repeat patterns you've seen before, which is viable in hardware now.
But following up on that, you just said for linked lists, it's very important that the access matches with the allocator. So if you know
most of the time,
so for trees, if you do a breadth first or depth first, that also determines how you walk the tree.
Well,
so
exactly,
could you then have custom allocators to help you, or?
And if you knew you were doing a breadth first search, you could allocate it in the order of a breadth first search. But that would involve doing a breadth first search.
Well, you're already instrumenting the code,
Yeah.
saying like, I want to do this prefetch. You could also just saying, well, I want to prefetch in this particular order.
I mean, not even if you knew the exact order you were going to, you would probably want to just allocate it in that order, right? And yeah, I think there probably is space for some hints like that. But unless you're working these data structures many times, it can be more expensive to do the reallocation, or even working out how to allocate something in breadth first order. Unless you can do it by construction, right? I think it defeats the point if you can go to.
All right.
have that as my final answer. I think it probably defeats the point of the breadth first search.
Okay, thank you again, Sam, for coming.
Thank
Wow.
you.